Hello, good morning. Hope you are all safe and stayed at home in this pandemic situation. And in compliance of university calendar of events, though the odd semester theory examinations are still pending, we are commencing even semester classes, of course, from home. And for this semester, I have been entitled to engage for your class paper 1, and in which the first unit, the solid state physics, has been allotted to me. Of course, this you have studied at PU level also, and for a chemistry student, probably in the third semester, they have come across solid state chemistry also. And there are four chapters are there. In the first chapter, you need to understand what is crystal structure, that is crystallography, in which lattice translational vectors, basis of crystal structure, types of unit cell, coordination numbers, Bravais lattices, all definitions are there, and the popular 7 crystal systems, Miller indices, of course some calculations and some problems you have to work out, expression for interplanar spacing. So based on which you need to work out problems not only in this chapter and for the forthcoming chapter also. And you have a detailed crystal structures of only two solids, that is sodium chloride and cesium chloride. And in the second chapter, you have crystal diffraction, X-ray spectrum, that is bombarding X-rays to a solid, what spectrum you are going to get, and in which two types of spectra you will come across, continuous spectra and characteristic spectra. And a very basic law, Bragg's law, of course qualitative derivation is not included for your syllabus. And finally, you need to understand how a Bragg's X-ray spectrometer works. And in these two chapters, you have problems. So 1 hour for first chapter and another hour for second chapter. So 2 hours problem. And in the third chapter, 10 mark question, either Einstein's or Debye's theory of lattice specific heats. So specific heat of solids in the beginning, experimental facts and classical theory, and Einstein's theory of specific heats of solids and Debye's theory of specific heat of solids. And finally, the free electron theory of metals, in which the classical free electron model, that's a Drude's model we used to call, and derivations of expressions for electrical and thermal conductivity, Wiedemann-Franz law, and failure of classical free electron theory. So this is the entire 4 chapters of first unit I am going to engage. Of course, the 5th chapter is semiconductor physics and then nanoscience, and that will be engaged by some other faculty. And as far as reference books are concerned, with the title solid state physics, we call it as the Bible of solid state physics, Christopher Kittle, which is Wishley Publishing Company, where you have very solid and beautiful 3-dimensional diagrams are there. Description is also very neat, but it is a foreign author. And another foreign author with the title solid state physics, A.J. Decker. These are the 2 best books of solid state physics. And Keir, that is also a good book. And the Indian authors, solid state physics with the title Kumar and Gupta, that's Pragati Publications, and solid state physics, Kumar, Gupta and Saxena, and that's the recent edition is very good. These are particular books to refer the content of solid state physics. But in general, to accommodate all the topics of your sixth semester as well as fifth semester, there are books with title Modern Physics. So Modern Physics by J.B. Rajan is also a very good book, and R. Murugesan, that's the most popular book, and Modern Physics by Dugal and Chabra, as well as R.S. Shankar Narayan. Apart from this, the Modern Physics by Saigal Chopra is also there. Many number of books are available, and as you know, I don't want to insist the books which are written according to the syllabus of either Karnataka University or Rani Chennamma University, because mistakes which are incorporated that you may not understand. And of course, the solid state physics, nowadays it is called condensed matter physics, after revolutionary and innovative techniques of nanoscience and nanotechnology. Condensed matter physics is a specialization. Earlier in post graduation, we used to have spectroscopy, electronics, nuclear physics, and energy physics, and this is solid state physics. And now in university level, that is at MSc course, now you are not having solid state physics, but it is renamed as CMP, that is condensed matter physics. So condensed matter physics is a field of physics that deals with the macroscopic and microscopic physical properties of matter, particularly solid and liquid phases, which arise from electromagnetic forces between atoms. So to the atomic level, you are going to learn, but basic for condensed matter physics is what the elementary solid state physics you are learning in this semester. Okay, these are the books I mentioned, and these are some photographs. Crystal cave of Mexico, gypsum crystals. They are measuring about 36 feet, that's 11 meters long, and weighing up to 55 tons, not kgs, 55 tons, which are considered as natural largest crystals. That just I am exhibiting the photographs, and this is from Chile, the cubic pyrite crystals, large gypsum crystals, and these are snow crystals. Just observe the cross section of the crystal. You are observing symmetry. Which corner you observe, the same arrangement, same orientation, the periodicity. Okay, and that is what the interesting property of a crystal. These are snow crystals, and lab grown crystals, the silicon crystals in the first photograph by the technique called Jokolsky technique at Baba Atomic Research Center, Trombay, India, and the right one, the largest KDB crystal, which is grown at Lawrence Livermore National Laboratory, United States of America. Of course, you know the matter is broadly classified into gases, liquids, and liquid crystals, and solids. But since we are dealing solid state physics, our discussion is confined only to solids, not with gases, liquids, and liquid crystals. So liquid crystal, you are very much popularly known LCD watches, LCD, that is a liquid crystal display. Most of the screens, most of screens of computer monitors and wristwatches, electronic wristwatches, where you are having liquid crystals have been used. But let's confine only to the solids. The solids, they are further classified into two types: crystalline solids and non-crystalline, one also known as amorphous solids. So these crystals were dealing in a separate branch of physics called crystallography, the study of geometrical forms and other physical properties of crystalline solids by using X-rays, electron beams, neutron beams, etc. constitute the science of crystallography. In crystalline solid, each atom or molecule is fixed at a definite point in space at a definite distance from and in a definite angular orientation to each other atoms or molecules surrounding to it. Usually a crystal is a solid composed of a periodic array. Array means arrangement. So periodic arrangement of atoms, we call that as a representative unit, which is repeated at regular intervals along any and all directions in a crystal. So very popular crystals: rock salt, quartz, calcite. Right. So what is a crystalline solid? That is the first category of solid. A crystal or a crystalline solid is a solid material whose constituent atoms, molecules or ions, they are arranged in an orderly repeating pattern extending in all three spatial dimensions, that is along x, along y and along z directions. So a crystal is characterized by a regular arrangement of atoms or molecules. You can observe in these two pictures. In crystalline solids, you are observing the periodicity of atoms at a regular distance, and whatever the orientation you look, it look like the same. Whereas in amorphous, the location of these atoms or molecules or ions, they are randomly positioned, randomly directed, and there is no periodic distance or any particular orientation is followed. So materials which are classified into two categories based on the arrangement of atoms or molecules. So this is sodium crystal. The crystal looks just like the diamond sugars, but you are observing a cube, a sodium crystal cube, green and the purple colored. So sodium and chlorine atoms which are arranged in a periodic manner. So examples for crystalline solids: in non-metallic crystals, you have ice, carbon, diamond, sodium chloride, potassium chloride, etc. Whereas in metallic crystals, copper, silver, aluminium, tungsten, magnesium. Likewise, you have many examples. And coming to crystal structure. So crystal structure is a periodic arrangement of atoms in a crystal. Association of each lattice point with a group of atoms. So that small group of atoms is known as a basis or motif. Of course, crystal structure is a combination of space lattice and a basis. That is a very basic equation you have to understand. But what is lattice? So lattice is just, it is also known as a space lattice. So in the space, infinite array of points. So in a space, infinite arrangement of points in which each point has identical surroundings to all others. That is called a space lattice or simply a lattice. So space lattice is not just arrangement of atoms, but it is lattice of points onto which the atoms are hung. Means on these locations, what the basis may be singular atom, or it may be group of atoms, molecules or ions. They are to be hanged at these lattice points. So the basic equation for crystal structure is, it is a combination of space lattice and a basis. As far as elemental solids, where the basis is a single atom, the example argon, and polyatomic elements, the basis is 2 or 4 atoms, whereas complex organic compounds in which the basis is thousands of atoms. Okay. So again, the same basic equation I have recalled here, lattice plus basis give us a crystal structure. So I have taken the example of sodium chloride. So you are observing the lattice in the form of a cube. So for a cube, you know 8 corners will be there. So at corners you have location of either atoms or attachment of molecule or attachment of ion. So it is a space lattice, and you have a regular periodic arrangement of points. Onto these points, the group of atoms, we call it as a basis, is hanged. So the combination of space lattice and group of atoms will give us a crystal structure. That's what you are observing. The structure of crystals can be described by lattice with a group of atoms allocated to every lattice point will give us a definite crystal structure. So crystalline solid, as I mentioned, the periodic, definite orientation, location of atoms, wherever you observe it looks the same. So the crystalline solid, you are observing the periodicity of arrangement of atoms in the space. This is a single crystal. So coming to the second category of solid, non-crystalline solids or amorphous solids. They are the solid which is composed of randomly oriented atoms, ions or molecules that do not form a defined patterns or a lattice structures. So these materials have order only within a few atomic or molecular dimensions. So usually amorphous solid is not extended for larger dimensions. It is very limited range of atomic and molecular dimensions. So they do not have a long range order, but they have varying degrees of short range order. The examples of amorphous materials include amorphous silicon, plastics and glasses. Amorphous silicon, of course, we are using popularly in solar cells and thin film transistors. So that is how the non-crystalline look, randomly oriented location of the points where the atoms or molecules are hanged. So we are observing the disorderness, right? And of course, there are some solids like B2O2 which exist in both crystalline as well as amorphous form. That's very few solids exhibit both crystalline as well as amorphous status. Okay, so let's go through some crystal properties, very important properties. Crystals have sharp melting points. They have long range positional order. They are anisotropic, that is properties change depending on the direction, whereas you have isotropic crystals. Iso means same, wherever you go wherever you observe, the properties remain the same. They are known as isotropic. But crystals are anisotropic depending on the direction. Okay, they have their properties, they are going to change. And crystals exhibit birefringence. So refringence, that is nothing but the refractive property. Birefringence, because most of the crystal, very popular crystals like quartz, calcite, you know, when you allow light to pass, double refraction is going to take place, ordinary and extraordinary light. So they exhibit birefringence. And some crystals exhibit piezoelectric effect as well as ferroelectric effect. Of course, piezoelectric effect. Piezoelectric effect means, for example, if I take a quartz crystal, which is probably either in a cube or a rectangular solid, so top and bottom faces, when you subject into a mechanical stress, what happens? The accumulation of similar charges takes place at the ends of the crystal. So since at the end of crystal, similar type of charges, all positive charges are accumulated on one side, all negative charges are accumulated on the other side, just because of mechanical pressure that you have applied between the ends of the crystal, and that drives electric energy. For example, you are very familiar to the wristwatches in which quartz is written. So inside it is not working with ordinary cell, it is quartz crystal. So for quartz crystal, as I mentioned, mechanical pressure when you develop, accumulation of charges takes place. With that you can drive electric energy, so the wristwatch runs. Suppose if you remove your wristwatch and put it idly for 3 to 4 days or a week or a month, the watch stops. Whereas if it is with the help of ordinary battery, it should run as long as storage of energy is there in the battery. But when you again put the watch to your wrist, again it start ticking. The reason is, when you are tying the watch to your wrist, so you know at the wrist our heart beat, the pulse. So usually when you approach doctor, where he is holding your wrist and he is counting your heartbeats, the pulse rate, isn't it? So those pulses are giving mechanical stress to the crystal inside the watch, so that it runs, and accumulated charges will be there for a longer period, so it may run even if you put the watch ideally. Okay. And whereas ferroelectric effect, you know, ferromagnetic material which is taken in the form of a rod, and when it is tied in the middle and applying the alternating electric field, what happens? Expansion, contraction, expansion, contraction at the ends of the rod, you are noticing set into very high frequency vibrations. They are used for production of ultrasonics. So you know the frequency range of infrasonics, audio and ultrasonics, that is sounds of frequency vibrating above 20 kilohertz, they are known as ultrasonics. So these properties exhibited by some of the crystals, piezoelectric effect and ferroelectric effect. You will learn you are having magnetic materials, so there you are going to learn these in details. So these are important properties of a crystal. So some terminology like space lattice, crystal, unit cell, basis. Okay, those words you are not supposed to get confused. Okay, so what is space lattice? I mentioned an infinite arrangement of points in this space. Each point has identical surroundings to all others, and arrays are arranged exactly in a periodic manner. You can notice the red points which are at regular intervals in a definite orientation, right? So that is called a space lattice. Translation lattice vector. So a space lattice is a set of points. So in this diagram you are observing just two-dimensional, only x and y coordinates you are observing. So space lattice is set of points such that the translation from any point in a lattice is represented by a vector. Just notations, I have used R, which is LA plus MB, where it locates exactly the equivalent point, that is a point with the same environment as point P. So R is equal to OP. So O I have not mentioned, that is origin, and end of the arrow, that is point P. This is a translational symmetry. The vectors A and B, they are known as lattice vectors, and L and M, a pair of integers whose values depends on the lattice point. So whether it is 1 unit, 2 unit in x direction or y direction, the diagonal of that is mentioned by this translational vector, which is equal to LA plus MB. So A and B, they are the vectors along x and y directions respectively, and L and M, they are integers, they are representing how many times in x direction and how many times in the y direction. So they are just the integers whose values depends on the lattice point. So to which lattice point from the origin you are drawing a translational vector, it is to be calculated with this equation LA plus MB. A and B, they are the vectors along x and y directions, and L and M, they are just integers. For three-dimensional lattice, it is LA plus MB plus LC. A, B, C, they are non-coplanar vectors in 3 dimension, that is along x, along y, and along z respectively. Of course, the choice of lattice vector is not unique. One could equally well take the vectors A, B, C as a lattice vectors itself. And basis and a unit cell. I mentioned a group of atoms or molecules identical in composition is called the basis or motif. Or in simple, you can say a group of atoms which describe the crystal structure, because they are those group of atoms which are hanged to lattice points will decide what is that crystal structure, right? That's a space lattice plus the basis. Basis is a group of atoms. So combination of these two will give you what crystal structure it is, right? So a smallest portion of a crystal, that's a group of atoms which when stacked together with pure translational repetition reproduces the whole crystal. So basis and unit cell. So you understood basis, a group of atoms which describe crystal structure, whereas the unit cell is a smallest component of the crystal which when stacked together with the pure translational repetition reproduces the whole crystal. So you have a lattice, definite locational points are there. To those points, group of atoms, ions, molecules are hanged or attached. So that forms one unit cell. So this type of unit cell stacked together with the pure translation repetition that reproduces the entire crystal. So in a crystal, you have many number of unit cell, and each unit cell is a space lattice plus what type of atoms are attached to the unit cell. So repetition of unit cells will give you the entire crystal. So this is a 2D crystal, only x and y coordinates you are finding. It is a 2D crystal. That's a plain crystal. Okay. So another example of a two-dimensional unit cell. I have taken the example of sodium chloride, orange and blue. You can take orange as sodium and blue as chlorine, or vice versa, but you are observing definite periodicity in a two-dimensional, that is xy plane. So choice of origin is arbitrary. The lattice points need not be atoms, but unit cell size should always be the same. So you can observe I have joined only blue in the form of a square, because this is two-dimensional. If you have three-dimensional, it will be in the form of a cube. Okay, it is just in a plane. So choice of origin is arbitrary, but unit cell size should be the same. You can start with sodium, or you can start with chlorine, it does not matter. Okay. This is also a unit cell. You can observe whether you start from sodium or chlorine, but close packing should be there. You have in the forthcoming topic the packing fraction. So based on packing fraction, you will come to know how strong that solid is, how weak that solid is. So some technical points will be discussed in the later classes. You see, the same atom arrangement I have taken, but this is not a unit cell, even though they are all the same, because empty space is not allowed. So again I am taking, I am recalling the crystal structure. It can be obtained by attaching atoms, group of atoms, molecules, which are called the bases, to the lattice sites of the lattice point. That is again the very basic equation, crystal lattice or space lattice, along with hanging group of atoms to these lattice points will give you a crystal structure. Of course, the unit cell and consequently the entire lattice is uniquely determined by the 6 lattice constants. We call them as lattice parameters. So you are observing x, y, z, the three-dimensional space, of course the origin, and I have taken one cube. For a cube, all these sides are equal in length. So along x direction, I have taken vector a, along y b, and along c, that is along z, the vector c. But you are observing against a, that is perpendicular to a plane yz, you have a. So the angle between z and y is represented as alpha. This specific convention you have to follow always, and perpendicular to xz plane, the direction of y, you have vector b, but the angle between z and x is represented as beta. Similarly, perpendicular to plane xy, the vector c is along z direction, and the angle between x and y, it is gamma. So a, b, c and alpha, beta, gamma. Of course, a, b, c you are familiar, they are vectors along the spatial directions, and alpha, beta, gamma, they are known as interfacial angles. So the lattice constants are in total 6. The vectors along x, y, z directions, and the angle between the three planes which are represented as alpha, beta, gamma, which are known as interfacial angles. So together these three vectors and these three interfacial angles, very important, they are known as lattice parameters. So based on these 6 parameters, as I mentioned, they are very basic lattice parameters. We define the primitives and different crystal systems. Of course, the primitives are nothing but, in this diagram, suppose O is taken as origin and the end of the cube, that is side OA, which is equal to small letter a, and OB is equal to B and OC is equal to C, they define the dimensions of the unit cell. They are nothing but edges of the cube. They are known as primitives, primitive vector. Whereas the angle between vector B and C and A and finally A and B, they are denoted by alpha, beta, gamma. They are known as interfacial angles. So depending upon these 6 parameters, you have different crystal systems as well as Bravais lattices. So first let us understand what is primitive cell. The unit cell, just now you observed a small cube which is formed by primitives A, B and C, is called a primitive cell. And remember, what is primitive cell? A primitive cell will have only one lattice point. Remember this. Of course, you have 8 corners in a cube, but this cube is in the neighborhood, it is closely packed with in total 8 such cubes, right? So a primitive cell is just a cube which has only one lattice point. So at the corner, each atom is shared among the neighborhood 8 cubes or 8 unit cells. So contribution of one corner atom to a particular unit cell is only 1/8. 1/8 to this, 1/8 to adjoining neighborhood. In total, for 8 unit cell, each atom at the corner is shared. Understand? So one lattice point, a unit cell having only one lattice point is called a primitive cell. If there are 2 or more lattice points, it is not considered as a primitive cell, it is called a non-primitive cell. So you can define primitive cell in another manner. It is a unit cell with all points in it only at the vertices, that is at the corners. As most of the unit cells of various crystal lattice contains 2 or more lattice points, it is not necessary that every unit cell is primitive. So you may find unit cells having more than 2 or 3 or 4, 8, 12, like that. They are not primitive, they are all non-primitive cells. Okay, in this diagram, space lattice is there. Of course, it is 2-dimensional. You can observe the first square, you have P is written, and here only at the corners you have location of atoms. Okay, this is primitive because at the vertices you have lattice points. This is also primitive. This is at the corners, it is not there, but it contains only one lattice point per unit cell. So it is also known as a primitive cell. One lattice point per unit cell. Such a cell is primitive. You can observe here, apart from corner, you have centrally localized one atom, there is one lattice point. So this is non-primitive, and apart from corner atoms, again you have adjoining atoms also here. So this is non-primitive, right? So a primitive cell contains only one lattice point per unit cell. Remember, lattice point is nothing but in a unit cell, as I mentioned, it is a cube. So that cube contains how many lattice points per unit cell. So lattice point is nothing but atoms, ions, molecules. So number of lattice point per unit cell is same as saying number of atoms per unit cell, number of molecules per unit cell, number of ions per unit cell. Okay. So crystal systems. We know three-dimensional space lattice is generated by repeated translation of three non-coplanar vectors A, B, and C based on the lattice parameters along with the primitive vectors and with what relation the interfacial angles are having among themselves. That is totally 6 lattice parameters. We can have 7 popular crystal systems which are shown in this table. It is a very popular question for 5 mark and sometimes it has been asked for 10 mark. For 10 mark you have to give description. For 5 mark, even if you write this table with mention of some examples is also enough. Okay, I will show you the table and I will discuss these systems in the next class. Just you go through 7 popular crystal systems. So 3 columns are there: crystal system, unit vector and angles. So 7 popular crystal systems are cubic, tetragonal, orthorhombic, monoclinic, triclinic, trigonal, hexagonal. These are 7 systems. But in each system, how the primitive vectors are related. So primitive vectors are edges of the cube, that is unit cell. So depending upon type of crystal, the length of A, B, C may be equal, may not be equal along X, Y, Z. So based on that the classification. Okay. Whereas in a cubic system, a perfect cube, so all the 3 sides are equal. So A is equal to B, that's equal to C. Whereas as far as interfacial angles are concerned, they are perpendicular to one another. That is alpha equal to beta and that's equal to gamma, each is equal to 90 degree. So such is a cubic system and some examples of a cubic system: sodium chloride, that is NaCl, calcium fluoride CaF2 and sodium chlorate NaClO3, right. And the second crystal system is tetragonal, in which A equal to B. So 2 lengths are equal, that is 2 sides of cube equal, but third one is not equal to either of A or B. As far as interfacial angles, here also they are equal to 90 degree. Alpha is equal to beta is equal to gamma, each is equal to 90 degree. Some examples of tetragonal: nickel sulfate and tin oxide NiSO4 and SnO2. And the third system, orthorhombic. So in orthorhombic, all the 3 sides of a cube, they are unequal. A not equal to B, which is not equal to C, and of course all interfacial angles equal, each is equal to 90 degree. And some examples of orthorhombic: KNO3, that is potassium nitrate, BaSO4, that is barium sulfate, and MgSO4, magnesium sulfate. They are the examples of orthorhombic. And then monoclinic. So in monoclinic, all the 3 sides of cube of unit cell unequal, and 2 angles are equal and each is equal to 90 degree. That is alpha is equal to beta, each is equal to 90 degree, but gamma is different, not equal to 90, it is other than 90 degree. And examples of monoclinic: Na2SO4, that is disodium sulfate, or in simple it is called sodium sulfate only, disodium sulfate decahydrate, and FeSO4, that is iron sulfate or ferrous sulfate. Okay, that is monoclinic. And a triclinic. So triclinic, all the three sides of unit cell unequal, and all the three interfacial angles are unequal and other than 90 degree. Alpha not equal to beta, not equal to gamma, not equal to 90 degree. Some examples of triclinic: copper sulfate CuSO4, and potassium dichromate, that is K2Cr2O7, right. And the sixth system is trigonal, in which all the three equal. This trigonal is also called rhombohedral or rhombic crystal. All the three sides A, B, C equal, and as far as interfacial angles are concerned, the angles are equal but not equal to 90 degree, but less than 120 degree. Alpha equal to beta, that is equal to gamma, not equal to 90 degree but less than 120 degree. The example for rhombic or trigonal crystal system is calcium sulfate. And finally, the hexagonal. Two sides of the cubic unit cell equal, A equal to B, but third one is different, and two angles equal and each is equal to 90 degree, whereas third one is 120 degree. Alpha equal to beta, that is equal to 90 degree, and gamma is 120 degree. The examples are silicon dioxide SiO2 and AZI, that is silver iodide. Okay, these are very popular 7 crystal systems, and these 7 crystal systems, they are further derived into 14 Bravais lattices. But what is a Bravais lattice? So in 1850, M.A. Bravais has shown that identical points can be arranged spatially to produce 14 types of regular pattern, and these 14 space lattices are known as Bravais lattices. So he has shown by arranging spatially the identical points to produce 14 different types of regular patterns, and these 14 space lattices are known as Bravais lattices. 14 types are there. So those 14 types and these 7 crystal systems. The first crystal system is cubic, which is having 3 Bravais lattices: simple, body centered, face centered. I will give the description in the next class. And the second crystal system, tetragonal, will have 2 Bravais lattices, simple as well as body centered. Whereas for orthorhombic will have 4 Bravais lattice systems, simple, base centered. You understand, the simple Bravais lattice is a simple cube only, which has only one lattice point per unit cell. That is what you can observe. The symbol used here is P. So P is primitive. Okay. So non-primitive is represented with a different notation. So orthorhombic, simple, base centered, body centered, and face centered. So 4 Bravais lattices will be there. Whereas for monoclinic, 2 Bravais lattices, simple and base centered. For triclinic, trigonal, hexagonal, they contain simple. So in total 14 Bravais lattices are there. So 7 crystal systems and 14 Bravais lattices. Okay, I will take the further details in the next class. So we need a board but because of lockdown we are not getting. Anyhow, till then I will continue with PowerPoint presentation only. Okay, hope you are following. If you have any queries, you can call to my number. Okay.